What's the latest project that's in your mind that has this unrelenting, scintillating pull to you, much like when you were in 2012 thinking about classical mechanics and you couldn't stop? You would even dream about it.
So once I've started doing this all my time, the mind hasn't been so pesky. But what I'm interested in right now, it's really this general theory of ensemble space. Basically, the
Ensemble spaces.
Ensemble spaces, yeah. And it really figuring out basic axioms. And again, right now, for me, the interest is to be able to do the argument of classical mechanics and quantum mechanics well. Basically, here's what I want to be able to prove. And let's do it like this. So we said before, right, that areas in volumes in phase space count the number of states, right? And they have a measure. They don't count the points, right? If I have discrete elements, you just count the points, and that's fine. But areas in phase space, right, when you are a continuum, you have infinitely many points. So you can't just say, oh, I have infinitely many states. Because then if you double the space, like double the volume, you would have the same number of states, which makes no sense. So you put mathematically a measure, and the measure is going to be additive. So if you take two volumes that are disjoint, and you double it, you're going to have double the size. Perfect. Now imagine that you have this volume, though, and you divide them in half and half and half and half. At some point, your count of states will become less than 1. What does it mean to have a region with less than 1 state? Means nothing. Not only, remember, if you have a uniform distribution on a certain amount of states, so the entropy is the logarithm of that number, right? If I have less than 1 state, it would mean I have a logarithm of a number less than 1, which is negative number. What does it mean to have negative entropy? Nothing. So this is where, in another way to say, okay, classical mechanics does not work because it tells me that there are regions with less than 1 state. What they say. Now, what happens is that if you do this analog, if you try to construct an analog of this, and I can't understand why nobody has ever done it, I've never seen it in the literature. If you do the same analog in quantum mechanics, you look at the entropy, how it goes. Well, the entropy of a pure state is exactly 0. And the exponential of 0 is 1, so every pure state counts as 1. And you can't have something smaller. But the state space of quantum mechanics is still a continuous. Like if you take the block ball, which is the 2 degrees, the surface is still continuous. So what happens if you take the surface of the whole ball and you say how many states there are there? There are 2. Because the entropy is 1, 2 to the 1 is 2. And if you take smaller and smaller region, you're going to have entropy that is less than 2. Sorry, entropy less than 1, but more than 0, which means counts of states less than 2 and more than 1. And you're going to go to 1, right? But that clearly cannot be additive, right? And there are basically these 3 conditions. You want to be able to count things, right? You want to be able to count states. And there are 3 things that you would imagine. One is that every state counts as 1. And if you have a finite region of phase space, of your state space, that should have a finitely many states, and you want the measure to be additive. Well, you can't have all 3, because once you have infinitely many points and you say every one is 1, well, the count of the region with additivity is going to go to infinity. And so you have to relax one of these. And what happens is that if you are in a classical discrete space, you relax that the finite region are going to have a finite entropy, finite count of states. So everything is additive and every state is counted 1. On a Lebesgue measure, what you do in phase space, you say, well, points are 0, but then I still have finite volumes and I have additivity. And in quantum mechanics, you say, well, I remove the additivity. And there are a lot of things that you can see that the weirdness of quantum mechanics comes from that additivity. But then you see, okay, why do I want to lose that additivity? Well, because I need to be able to count states. Every state must be 1. And a finite patch with infinitely many states on top of it, if I make a mixture of that, I still need the finite entropy, finitely many states. And so this is what I like to say, that there is only one way to create ensembles that have an entropy and a count of states such that I have a measure defined on a continuum, the count state, but it has a lower limit. And so the quantization in my mind is really putting this lower limit to the count of states. Classical mechanics does not have, because you can make things smaller and smaller and smaller. So you take one state, chop it, chop it, chop it, chop it. In quantum mechanics, the quantization is I can't have less than one state. And so when you go up, things are going to look additive. Things are going to look classical. But when you go small, no, that you have this lower bound. And just to tell you, and so this is what I'd like to have in this ensemble spaces. I'd like to be able to run that argument. But I want to be able to create this structure in a way that I'll be able to use for field theory as well. And that's a challenge because it's the whole problem of infinity. And I want to try to see if I have a path for quantizing space-time as well and leave it as a possibility. Because in space-time, you're going to have the same problem. You say, I have a field theory. Now, I count the number of states, in each field, but then I have to count the number of degrees of freedom. And in particle mechanics, it's finite. I count them 1, 2, 3, right? But in a field theory, you have a field for each point of physical space. And so now you have, sort of continuously many degrees of freedom. Now, you can't say that they're infinite. That wouldn't make sense, because if you double the region of space, now you would have the same number of degrees of freedom. It's always free. No. So what's going to happen is that you need to put a volume measure on space, and you say, if I double the volume, I have doubly many, twice as many degrees of freedom. Right?
Well, why don't you just use I've mentioned this before, the Bekenstein bound.
I need things to go smoothly to zero. I can't just say at some point things become discrete, because that's not what's happening. What's happening is that I have something where I still have, all these dense states. Quite frankly, it doesn't even matter if it's real or rational. The important thing is that you have dense sets, and you need to count the elements in the dense set. And you can't just say that they're infinite.
All right, Gabriel, so we talked about philosophy, math, and physics. Let's talk about math and physics. Where does that line lay?
Okay. Yeah, so the line between math and physics is something that I, had to think a lot about, because since I want to have this sort of rigorous axiomatization approach, I need to understand how do they do in math and whether the way that they do in math is actually good for physics, if it's enough. And one of the things that we have sort of a wrong impression in physics or in engineering is that math, it seems all so elegant or pristine and so precise. And it feels like everything is there and we should imitate math in some way. But this is kind of never going to work, because the way that math is able to be rigorous, like the way that they did it, is essentially to remove all the parts that are difficult or impossible to make precise, and remain only with the formal structure, the syntactic structure, that you can actually be precise about. So there are sort of a lot of things like what are called semantic paradoxes, like something like...
there's the largest number that can't be described,
yes.
Or there's the smallest number that can't be described in so-and-so amount of characters.
Exactly, right. So that's something that if you have meaning, right, meaning is attached. Meaning is always this very fuzzy things, and it always allows you to create some things like that. And so what I guess the formalists decided, Hilbert I think was the one that pushes for this, you say, okay, we'll forget what the meanings are, we just have some symbols, they have some rules, and that's it. That's all that we're going to describe in mathematics. And a lot of mathematics is now thought in that way, in one way or another. And in a sense, that's sort of where the power of math comes from, because if you talk about, I don't know, a Boolean lattice, for example, well, that same structure could be representing sets of statements, so a logical structure, or sets of sets, or it could have, like, physically could even describe the systems and subsystem relationships. So you can study the mathematical structure, you can study the equations, regardless of where they come from, physics, biology, economics. So in the end of the day, to the mathematician it has an advantage to just drop the meaning, because then their tools are more powerful because they can be applied regardless of the meaning. And in physics, we can't do that because we have that pesky connection with experiments. And so we can't just manipulate symbols in any way, whatever. We need to know that that symbol corresponds to a specific system prepared in a specific way with the things that we measure as specific things. So we always have an informal system in physics. You can't just get rid of it. And so what the challenge is not saying we're going to put everything in the formal system, because it's never going to happen. The experiments are not going to suddenly become symbols. You need to define what is advantageous to put in the formal system and what is not. And that's the hard part. So it's not a question of whether you can do it, but it becomes sort of a technical problem, sort of an engineeristic problem in how can you do it efficiently. Essentially, the game is to find the minimal set of axioms that you want, that you need, actually, in the form that it's as easily justifiable from the physics. Because that surface, right, that line in between, when you take physical, informal things and you put them in the formal things, that's where the things can go wrong. Once you are in the formal system, you have the math to help you. And so those parts, and that's the part that I'm interested in physical mathematics, getting those definition and justification right, it's the part that is the most difficult. And it's most difficult because I have a feeling, and I can't, I'd like to be able to have a proof for this, but again, you can't, because it ties in things in the informal system, so it's difficult to create a proof for that. I'd like to have a tight argument that shows that whenever you're taking something from the informal system to the formal system, that is my feeling, you are always going to make some kind of simplification. And so even a simple concept like, whether something is an orange or not, right? You go to a supermarket, you can easily identify what is an orange and not an orange. Right? So it seems natural that, oh, that's a true, false statement, very easy. But if you think how an orange develops, starts with a flower, gets pollinated, and that, right? And there is no point that you can say, oh, this is the instant where it actually became an orange, right? So all these concepts that we have are fuzzy, and you're going to have to make a cut. And so if you're talking about objects in a supermarket, yeah, perfectly fine, because we're not going to have these in between. And so it's going to be either true or false. But if you're studying biology, you're not going to, that statement is going to be ill-defined. So even defining this property, even defining the statements themselves, I don't think there is a way to define statements that are universally applicable in all circumstances. It's always a matter of, I have a realm of applicability, a domain, and in that domain, in that context, that statement makes sense.